Aeration dynamics. We said earlier that aeration is not a process that runs a steady state. And even if you were, the power company does not run a steady state. So there is a dynamics within the process, and there is the dynamics of the electricity that feeds the aeration process. So what happens inside of an aeration tank? It is a typical aeration tank with a pre-anoxic zone. So this will be the process for nitrification and denitrification that we all know as LE. And it's indicative of most, of many plants, but most processes behave just like this one. You have an anoxic zone or an anaerobic zone where the readily biodegradable fraction of the COD is sorbed onto the biomass. In this case, the biomass uses it for denitrification. But then the rest of the COD goes on to blending on bubbles. But as the process progresses going to the right, the COD is removed and the dissolved oxygen goes up in profile. So you'll have an ascending profile of dissolved oxygen and a descending profile of the load. So the denitrification zone already serves a good purpose, which is not only to use part of the load, but selectively to use the part of the load that will land on the bubbles and reduce oxygen transfer. That's the readily biodegradable COD. Now, how do we calculate the oxygen requirements so we know how much air to apportion to meet these oxygen requirements? Well, the oxygen requirements are the product of the flow rate of the water going in and the in minus out, the delta, the amount of load we need to remove. And the load being defined as the carbonaceous load, so the delta BCOD, and the nitrogenous load, which is 433 delta ammonia. 433 is the conversion of units of ammonia to unit of oxygen. Now, if you do a denitrification process using the carbon that comes in from the influent, then that 433 becomes a much lower value. And at the end, we have minus 1.42 px bio being the amount of biomass, VSS, that every day is being wasted, okay, and does not contribute to the oxygen requirement because you grow bacteria just to the same extent as you waste. 1.42 converts the units of solids to the units of oxygen. Now, our job is to exceed the oxygen requirements, otherwise we wouldn't have any residual dissolved oxygen. The dissolved oxygen is the little leftover that we have in the process above the oxygen requirements. Now, if we want to be energy efficient, we either avoid over-aeration or lower the way we have to provide the oxygen by changing completely the process. The process for like deammonification, for example, the process that are promoting simultaneous nitrification, denitrification, do not have this kind of oxygen requirement. So this is for a fully aerated process, the more traditional type of process. Now, I travel around the world a lot, and every time I look at a label of a personal care product, I always notice that after water, the number one component immediately following is surfactant. So these are the type of contaminants that we, in domestic wastewater, put down the drains, and we're feeding to the wastewaters that reach treatment plants. So this type of contaminants are also part of any household product, like detergent for the washing machine, dishwasher detergents, you name it. And they're not placed there with a pernicious intent. They're there because their job is to dissolve grease and make sure that it gets washed out. But these are all surfactants. And if you look at the ingredients on any detergents, when posted, surfactants will be the majority of the content because that's what they're engineered to do. But what they also do, the surfactants have an amphiphilic structure. They have a polar head and an hydrophobic tail. So this form my cells that can lift the grease stain from my shirt, and then I can wash it off. Okay, so I can disperse it in a water solution, even though grease and water are immiscible, and I can wash it off. That's good purpose. But we tend to overdose these surfactants so we can have a very effective wash. And so what happens to the residual surfactants that are not attached to grease, they either attach with each other, okay, or they form micelles. When you reach the maximum concentration you can have for free surfactants, it's called the critical micelle concentration. And you can have also free surfactants at the interface between water and air. This cartoon shows at point B that you have the polar head, it's in the water, and the tail sticking out in the air. If we could look at the surface of water once you have soap in it, and if you don't make foam, it will be a flat surface, and the surface will look like the fuzz that is on the skin of a peach. We can't see that, but that's this cartoon illustrates the concept because the tails just repel water. Air is just not water, that's good enough. So what happens once I have a nozzle releasing bubbles? The surfactants are floating about in the water, minding their business, and then the bubble interface offers a volume that is made not of water, and so the surfactants migrate right away to the surface of these bubbles. If these bubbles are fine bubbles, 2, 3, 4 millimeters, like the ones from fine pore diffusers, by the time they detach, the surfactants already reach their equilibrium concentration at the surface. So the bubble travels with this straitjacket. Normally a bubble will have the gas inside circulating all the way to the surface, keep rejuvenating that driving force that drives oxygen transfer. With the surfactants, there is a stagnation film caused by those tails, and now the rejuvenation is much hindered. That causes the alpha factor to be below 1. So let's revisit the terminology. The oxygen transfer efficiency is mass transfer per mass fed. The oxygen transfer rate is mass transfer per time, so it's actually our design criterion. And the aeration efficiency is the mass transfer per unit power spent, so it's our more economic indicator. At standard conditions, we have 20 degrees, 1 atmosphere, 0 DO, and clean water, okay? And the salinity is below 1 gram per liter. So all of this correction end up having an S. At process condition, we don't have the S. But if I go from process to standard, that standard that is for clean water. The process is in wastewater. So I also need to introduce an alpha factor when I correct the standard condition in process water, okay, which is different. Now, 0 DO means that the driving force is 0, because depending on the driving force, different processes will have different performance. It's very difficult to put the last molecule of oxygen, whereas it's easiest to put the first molecule of oxygen when there is none in the water. So to make sure we compare everything to a level field, 0 is 0 for everybody, since saturation depends on the location of the test. The alpha factor is between 0 and 1, and the pressure is used with elevation, a mean sea level. The temperature, we use 20 degrees, and the zero salinity means less than 1 gram per liter, which is like tap water, so it's potable. So we can find that water anywhere. We can never do a test like this with effluent water, because effluent water has some residual organics in it. We never clean it to 100%. It's impossible, okay? So the correction to standard condition, but in processed water, okay, always results to have a value lower than clean water. So if clean water is 100% of our performance, processed water will be 30 to 70% of that value, and varies highly within the day and along the process. So bubbles could be small, could be large. The picture here shows small bubbles being released by a fine pore diffuser. Now, the bubbles are released, and if there is more pressure in the air inside than the hydrostatic head plus the pressure drop, the bubbles are released with an initial velocity. So the bubbles are released in a jet area, and after the jet zone, the initial velocity is dissipated, they slow down, and eventually reach their terminal velocity, and they keep wobbling about in a plume. So the jet area doesn't really transfer much oxygen because it's saturated, but the plume is what really transfers oxygen. So as soon as you exhaust their initial velocity, you slow down to their terminal velocity. If the bubbles are released with a pressure that is just enough to overcome the pressure drop and the hydrostatic head, what happens is the bubbles form and detach, and they start accelerating until they reach the terminal velocity. But the terminal velocity stands. The bubble expands going up, so the terminal velocity goes up going up, obviously. Alpha is a function of the bubble, not of the diffuser. So depending on the size of the bubble and the speed at which it's released, alpha will be determined. So if you look at two diffusers releasing the same bubble, the alpha should be the same. But diffusers age differently. Their material will have different fouling, different material degradation, and the size of the bubble at detachment is the equilibrium between the surface tension of the bubble and the buoyancy. Once the surface tension is not enough to overcome the buoyancy, the bubble detaches. Okay, if there is an initial velocity from the pressure, that obviously contributes to overcoming the surface tension. But if you have the diffusers, two diffusers, they will release the same bubble as new, but they age differently. Their surface tension will be different at the pore, so you might have different alpha over time. Coarse bubbles and droplets, when splashed up in the air, have a very high interfacial velocity. So their oxygen transfer efficiency is low because it costs a lot of energy to produce this. Okay, but you can have a high oxygen transfer rate. So at the expense of efficiency, you can have a high transfer rate. That's why they're typically used for industrial treatment where you need high rates because you have highly contaminated water. But fine bubbles are preferred for municipal, for urban wastewater treatment because they're energy efficient and we don't have high strength wastewater in general. So they have low interfacial turbulence, they're slow, they provide a lot of chance for the accumulation of surfactants, but they have so much surface area they can still dissolve a lot of oxygen, and the transit time is much longer, there is more contact time. So there's a high oxygen transfer efficiency, even though the oxygen transfer rate is somewhat limited, but it's sufficient for treating municipal wastewater. So this alpha factor, this notoriously mysterious alpha factor, is the ratio of the gas transfer coefficients in processed water and clean water. The SOT is the value we get from the manufacturer with a warranty about the aeration system's performance in clean water. What the design engineer must do is to combine the two. The design engineer comes up with the alpha factors, not one but a range, okay, for each one of the reactors. And the SOT is a function of the airflow rate and the diffuser density as specified by the warranty documents. So the alpha SOT, the product of the two, is what we design with. And when we go to the field to measure it, we measure that aggregate. We don't measure the two separate. So alpha is variable and not a constant. Let's remember this forever. It's variable. It cannot be constant because the airflow rate changes as a function of the load. The load is different, the alpha is different. The bubbles change their size and the accumulation of surfactants is different, okay? So what we should talk about is the flow weighted average of alpha when we compare things, not the instantaneous alpha, and also the average alpha throughout the volume. So there's a lot of averaging that takes away the differences within the volume of a reactor, for example. For fine pore diffusers, alpha, it's very low, typically at the beginning of the process, and escalates to a much higher value towards the end of the process. And if the fine bubbles are released by a jet, the alpha is same as the fine pore diffuser, because a jet, even though it's a mechanical system that injects the bubbles very quickly, the part where the bubbles travel as a jet have very little transfer. The transfer really occurs in the plume when the bubbles reach their terminal velocity. And regardless whether a fine pore diffuser or a jet injects it into the water, the terminal velocity is the same because it's a function of the size of the bubble. And in coarse bubbles, the alpha is slightly higher, but it comes at the expense of a much lower SOT. So the alpha may be a little higher for coarse bubbles, but the SOT is way lower. So overall, the product of the two is in favor of fine pore diffusers. But the oxygen transfer rate in total mass you can transfer, at some point you run out of space to put diffusers on the floor. So that's limited for fine pore diffusers, of course. So different loads every hour of the day have different alpha. And if bubbles coalesce in sludge, the alpha drops. The reason is alpha is the ratio of KLAs. The little a is the surface area. So if bubbles coalesce, they accelerate, all right, but they lose a lot of area. So the A plummets. And this happens when you have a sludge that is very thick, such as in digesters or membrane bioreactors. How do we use the alpha factor? So first of all, let's remember that the oxygen transfer rate, and only look at the units. The units tell us everything we need to know about all of these equations. The kilogram of oxygen we transfer in the water needs to be more than the requirements and what we need. Otherwise, we don't have any dissolved oxygen. So the oxygen transfer rate, which is the kilogram of oxygen we transfer in the water per unit time, are equal to the oxygen feeding rate, WO2, which is that oxygen in going to the air, okay, times the efficiency in percent, which is the mass transfer per mass fed, okay? The units are consistent. This means that the oxygen transfer rate is proportional to the airflow rate, because WO2, the amount of mass of oxygen that is in the air, is proportional to the airflow rate, because it's just the density of the air times 23%. And the same alpha SOT. So if I turn around that equation and I solve for airflow rate, the airflow rate I designed the blower house for, okay, how much air do I need? Is proportional to how much oxygen I need in the water divided by the efficiency. Now, we said that alpha changes every hour of the day, so that denominator changes every hour of the day. Now, if I look at the blower power equation, there is an adiabatic equation there, but let's make it much simpler. Let's just look at the proportionality, okay? So the blower power is proportional to the airflow rate, okay? It's also proportional to the pressure drop, but to a small exponent. So let's simplify this for sake of simplicity. Blower power is proportional to the airflow rate. But from the previous slide, we saw the airflow rate is proportional to the oxygen transfer rate divided by alpha SOTE. But if alpha SOTE becomes a smaller value because alpha is smaller, either due to fouling or because certain hours of the day, to get the same oxygen in, I have a different type of load, and the load will be more concentrated and in surfactants. So smaller amount of larger load, smaller number for alpha, larger airflow rate to get the same oxygen into the water. And that's the reason why blowers have to keep putting more or less air during the day, way more in proportion when you have a higher load. This is a 24-hour monitoring of a plant. Just to give you an example, the green points represent the airflow. You see that the airflow goes up as the COD on the horizontal goes up. And as the COD on the horizontal goes up, the alpha goes down. Now, this is a test done in one plant. After having repeated this in multiple plants, we have very high confidence the alpha can change as high as twofold over 24 hours. The COD there changes only because during the day we're on the far right and during the night we're on the far left, and it keeps moving, swinging back and forth because you have your diurnal cycle. So you should expect as your flow goes up and your load goes up, the alpha should be the reciprocal, okay, like a sinusoid reciprocal to the load curve. And this is the monitoring done with an automated off-gas analyzer. This measures the gas coming out of the aeration tank. So we put 21% oxygen in. What comes out is less than 21%. And on the left-hand side there, we see that we have an oxygen transfer efficiency that oscillates about twofold every day. It's maximum certain hours and minimum other hours. Maximum certain hours, minimum other hours. And it's always minimum the oxygen transfer efficiency when you have more off-gas flow. You're putting more air to the water. Why do you put more air to the water? Because there is more load. If there is more load, the controller tells the blower house, we need more air because the DO goes down. And you need more air because there's more contamination. That's why the DO is going down. With time, diffusers foul. All diffusers foul. There is no diffuser that is fouling proof. Maybe they retard the foul to a later time, it's slower, but all diffusers foul to some extent. And fouling is a combination of the biological fouling, which we tend to use interchangeably as the word fouling, but it's really biofouling, and also the scaling, which is the inorganic precipitation. So there is fouling and scaling, but at the same time, this happens particularly for membranes that are elastic. With time, the diffuser's material ages and the membrane becomes stiffer, they elongate, the pores may become stiffer, they don't open at larger airflows and they don't close at lower airflows. A lot of aging occurs in materials over time. And so the combination of all of this produce a degradation of efficiency. So if my alpha SOTE at the beginning was a certain value, with time that value is lower. And the ratio of that with time, we define the fouling factor F, which is the alpha SOTE after time in operation divided by the initial alpha SOTE. So now we have an alpha F value over time. Okay, and that fouling factor needs to be factored in when we design, because we need to think about the aeration system shouldn't just work today. It needs to be able to work over time. At the same time, all the fouling and scaling and the material aging of the diffuser may increase the pressure drop of the diffuser, which affects the way the operating point of the blowers. And therefore, we also need to define the pressure drop over time divided by the initial pressure drop. And we introduce a ratio, that factor called psi. Now, this is an example of tracking diffusers fouling over a period of about 15 months. And what we see is as time in operation progresses, all the diffusers regarding the geometry, regarding the material, their efficiency goes down. Their alpha F goes down. At the beginning was alpha at time 0, and it becomes alpha F with time. F is the ratio of these curves to the initial point. Okay, so if we define the value F as alpha F divided by alpha, it will be 1.0 at the beginning and less than 1. Okay. And why is that? Because there is bacteria forming biofilm, and you see the biofilm mature to a steady state, to a steady level, and at some point the bubble's got to come out somewhere, but it's very inefficient. So the efficiency in a year and a half, it could be as low as half of what it was a year before. So half the efficiency means more than twice the air, because if you put twice the air, well, first of all, the air comes out with larger bubbles now, so it's less efficient in terms of SOTE. So all of this is linked. Alpha and SOTE. So with less and less efficiency due to fouling, you need way more in proportion to compensate efficient airflow, okay, on the other side, which means more kilowatt, more cost. So let's look at the characteristic curve of diffusers. When you buy a brand new diffuser, you get an airflow rate curve, a curve on airflow rate on the horizontal and SOT on the vertical. But when the diffuser it's in wastewater, now you have alpha, right? So the value is lower than clean water. So if that white line is for a new diffuser in wastewater, in clean water, that white line would just be higher because the difference is the alpha factor. The product of the airflow rate times the alpha SOTE, that rectangle is the oxygen transfer rate. That was one of the equations earlier, right? It's proportional to the oxygen transfer rate. So that's how much oxygen you need in the water, and you desire to have that to overcome the oxygen requirements and leave some dissolved oxygen. With time, the diffuser performance goes down. So the ratio, the dashed to the solid line is the fouling factor F. Now what happens is due to fouling now, this value went down, but I cannot just cut piece of that rectangle to a lower efficiency because I have too little oxygen. So the controller that operates the aeration system and makes sure that you always meet the dissolved oxygen doesn't know anything about this. The dissolved oxygen goes down, releases more air to compensate. This is what the controller does, releases more air to compensate and to get the same dissolved oxygen in the water. Now I need more air because I have less efficiency. You see, the area of the two rectangles are the same. And what happened is I don't just go down to the yellow extent, but to the red one, because now I'm in a less desirable operating point with more airflow, okay, over time. So I have a lot less efficiency in proportion. If I look at the pressure drop of a diffuser, when you have a new diffuser, whether this is in clean water or wastewater, you have the same pressure drop, okay? The diffuser pressure drop is the same. Now, with time, that pressure drop increases because the diffuser is fouled, right? And there is some scaling, there is material aging. So now the pressure drop goes up. So what happened is you would expect, due to fouling, the pressure drop to go up. But remember from the previous slide that now I have to operate the diffuser at a higher airflow rate to compensate for the loss of efficiency. So this is the effective pressure that I need to front and to overcome to get the bubbles out. So when I do the design, I don't just have to inflate the pressure requirement by the yellow extent, but by the red extent, thinking that in the future, the diffusers need to, will have that pressure drop. And the blower needs to overcome that pressure. If you don't have enough efficiency or you don't have enough air, the plant will just not have enough oxygen. But if you don't have enough pressure, the plant will not have any bubbles. Bubbles will just simply not come out. So it's very important to consider that this is a logical indicator, either or. You either have enough pressure or you don't, okay? Whereas the airflow rate is a proportional indicator. Let's go back to the blower house and look back at the proportionality. So the blower power was proportional to the airflow. And earlier I said there was also a correction for pressure. Let's bring it in. So the blower power is proportional to the airflow that the blower discharges and the pressure drop of the discharge of the blower to the exponent 0.283, which is the adiabatic compression ratio for air. Now, the airflow is proportional to 1 over alpha FSOT. We saw that earlier when we look at the equations, right? And we introduce now F in yellow because with time, that's even lower. And the pressure factor psi, is the ratio of the pressure time T divided by the initial pressure. So the airflow goes up because the denominator becomes smaller, okay? And the pressure goes up because the numerator becomes larger. So over time, the blower power goes up. Over 24 hours, we have this change in alpha, which could be twofold. This is in the orange points are from a treatment plant, measurements done over 24 hours, and the black line are from the Benzig et al. Model, which is a predictive model of alpha as a function of COD, okay, as a function of COD indicators. So this is an effort in modeling, and during the modeling module, you will see more of this. If you use an alpha that is constant, you are at the two boundaries of this shaded area. The top boundary is a cautious scenario. You use a lower alpha. It's a constant for each one of the 3 aerated reactors. So it's better than a constant throughout the plant. But it's a very rigid type of concept because it's a constant value for something that we know it's dynamic. Okay. So we pick 3 constant values for the first reactor in the cautious scenario: 0.4, 0.53, and 0.67. And with an F built in, with time, it will be 0.3, 0.4, and 0.5. That's more cautionary, okay? And that means that you have the maximum amount of air being discharged just to make sure you get the dissolved oxygen. The optimistic scenario is somebody who thinks that there's not going to be very much fouling and the alpha is going to be pretty good because the contaminants are not so bad. And so you're going to have an alpha F of 0.5, 0.6, and 0.7. In reality, what happens is you're in between. And you're in between every hour of the day. At the minimum load, you're probably close to the optimistic scenario because you see the black line reaches the optimistic scenario only in the minimum load, which is really when the alpha is the highest value. But at the highest load, the alpha, it's much lower than the optimistic scenario, and you see the black line departing from it and getting closer to the cautious scenario. Now, the cautious scenario has a lot of safety factor built into it. So the wastage is really between the solid black line and the shading all the way to the top. That's all wastage. But the area between the solid black line and the bottom shading, that will be oxygen deficiency if we use the optimistic scenario. So for lack of better information, the design engineer will pick a cautious scenario because the rule of design is if you over-design, you might be yelled at, but if you under-design, you might be sued. And so you'd rather be yelled at and make sure that it works. These are three examples of modeling this simple process, 2 anoxic tanks and 3 aerated zones. The past scenario was a fixed alpha over 24 hours. And now there are simulators that allow you to schedule the alpha. You do a characterization of the load, you may do it several hours of the day, so you create a curve for the load, you can measure your alpha, you can enter it as a schedule for weekdays and weekend. Hopefully you can have this kind of information for a cold season and warm season. That would be wonderful. But what if you have an upset because of a storm event or a return flow that is unscheduled? Whatever is not scheduled, the simulator who does the model for you will not know. And so when you design, you cannot predict these events. In the case of a predictive scenario, when the alpha is estimated as a proportion of the COD going into the process, then you can have a much higher confidence in your alpha. Now the 3 lines are because there are 3 aeration zones. So the higher of the 3 alpha is always the last one because there is less load. So aeration 1 is the lowest alpha, and then the medium and the highest. And you see the shading in the colors. They go from the darker, the medium, and the brighter ones for all the 3 graphs here.